All right, welcome back to the lab for this week. This week we're going to be focusing on one of my personal favorite things, which is hydraulic conductivity and its variability in natural geologic materials. As we've seen in class, this is a hugely variable property, and it's something that really controls how groundwater flows in the subsurface. So it's something we'd really like to know well if we want to make predictions about contaminant transport or things like that. We're going to be working with estimating hydraulic conductivity using this device, which is known as a permeameter. And a permeameter is basically a way to hold a sample of porous media in a volume like this, and to be able to estimate the hydraulic conductivity based on measuring something about how water flows through it, or the speed with which water levels drop in a burette, something like that. So we'll see a few different methods of using this permeameter during the lab this week, which will include the constant head and falling head method for hydraulic conductivity estimation. All right, to start with, since you're not getting a lot of hands-on time with anything in labs these days, unfortunately, I thought I'd at least walk you through the steps of putting together a permeameter and thinking about how it works. So this is the base of a permeameter, and you can see we've got an outflow here, and you can see we've got these rods that are essentially going to be support for our system as we're setting it up. The next thing we have in the permeameter, and this is especially important for samples that consist of unconsolidated material, is this porous stone here. Basically what this is it's a bunch of stone cemented together with tar or something like that, but it has a very high hydraulic conductivity. It's very easy for water to get through this. And that's important because we want to be measuring the hydraulic conductivity of our sample, not the hydraulic conductivity of this porous stone. So we put the porous stone at the bottom to keep any sand or things like that from leaving our permeameter. And the other thing I suppose I should point out is these rubber rings on the permeameter. So if you look at this side of it, you can probably see right around here, there are some rubber rings that are going to be helpful for keeping a seal in our permeameter. I always like to think of things that could go wrong or things you should be careful of when you're measuring, when you're working with these in the real world, when you're working with any equipment in the real world. And this is one thing you have to be careful with permeameters. Because we're going to be trying to measure things like fluid volume that's passed through a sample or head, we need to be careful that we're not losing volume, i.e. leaks. Anyway, so here's our sample holder. And so you should be thinking of the Darcy experiment, where we have Q equals Ka dHdL. And this is going to be our area here through which we allow flow. And it's nice and clear so that we can get a sense of the sample we're working with. Anyway, so back to assembling my permeameter. So we're going to take this porous stone, I'm going to put it at the bottom of the permeameter, and then we're going to put my sample holder on top, so that the porous stone is sitting at the bottom, and now I've got these rubber rings which are going to be compressed up against my sample holder. In some permeameters, the rubber rings are removable like this. You might have gaskets like that. These ones, they're built in, so you don't have to worry about it. Now the next thing we're going to do is we're going to want to make sure we don't have any leaks at the top. So we've got a second ring that we're going to attach here, and this also has a rubber gasket on the inside to prevent leaks. So we put that on top here, and when this is pushed down by some bolts here, this is now going to create a tight seal. It's going to keep water from getting out any other way than through this hole here or this hole that's going to be at the top. All right, so I've got most of my permeameter assembled here. If I were doing this experiment for real right now, I would go with a wrench and make sure that these were tight enough so that I didn't have any leakage along the inside here or along the outside there. I could even close this valve at the bottom to make sure that this would hold water perfectly. I'm not going to fill it with sediment just because it would be messy, it would take a lot of time, but hopefully you get the idea there. So we have to imagine that we've now filled this column with sediment, and we're going to have water coming in the top of our permeameter. Now, if there was nothing holding the sediment in place, that sediment might flow around and not behave the way a porous media in an aquifer would. So we're going to put another porous stone at the top of our sample, and that'll provide some compression to keep the sediment where it is. So you have to imagine this a little bit, but essentially what I would do is I would put another porous stone in here, and then I would put this cap on top. And notice the cap also has a rubber gasket, and it has this spring that's providing just a little bit of pressure to keep the sample from moving, to keep it in place. This is a fairly simple permeameter. It's meant to be used for sort of near surface conditions. There are permeameters that people use for high pressure experiments where they want to look at how, for instance, a rock's permeability would behave under deep pressures, in which case you wouldn't just have a spring, you'd probably have something a lot more substantial than that. But anyway, if you imagine this porous stone on top and the spring, then what we would do is attach this again, and again, just tighten each of these so that this topmost rubber gasket comes into seal with the sample holder underneath. And there you have it. We're done with our permeameter assembly. So now if you imagine, again, Darcy's experiment, we've got our cross-sectional area through which there's going to be flow. We've got a length we can measure across which there's going to be flow. And now what we need to do is we need to set up a head gradient, and we need to measure the flow going through.
In the first portion of the lab, we'll be estimating hydraulic conductivity for 3 different sediments using constant head setups. The funnels at the top of these experiments represent the elevation of the upper constant head reservoir, and the lower location of constant head is the outflow of each permeameter. In the first case, water is flowing upward through the sample since the higher head reservoir is connected to the bottom of the permeameter. In the second case, the inlet from the funnel is at the top of the permeameter, resulting in flow downward through the sample. And finally, in the last case, the upper constant head reservoir is causing horizontal flow from right to left. It's worth taking a look at how we ensure a constant head at the upper reservoir. Notice the overflow tube at the side of the funnel, which will allow water to bypass the sample and maintain a consistent water level in the funnel. This allows our sample to truly be under constant head conditions. To make calculations for hydraulic conductivity, K, we use the form of Darcy's law shown here. We need to measure the inlet and outlet heads, the length of the sample, and the sample area. Keep in mind the units for all quantities. For example, A has units of area, length squared, and take care that all measurements use consistent units. For the upper head reservoir, the water's surface is where total hydraulic head is exactly equal to elevation head, since fluid pressure is atmospheric. We can thus measure water level above a datum, such as the bottom of our experimental sink. We use the same approach for the outlet hydraulic head. Here, again, pressure at the outlet is atmospheric, and therefore the total hydraulic head at this point consists purely of elevation head. When measuring the length of the column, we assume that all components of the system, including the permeable porous stones, contribute negligible hydraulic resistance. We therefore measure the length of the column consisting entirely of the sample sediment and nothing else. We also must measure the cross-sectional area through which flow is occurring. In this case, since the permeameter is circular in cross-section, we can measure the diameter. Finally, we need to measure a flow rate through the sample. Assuming that the flow rate is steady throughout the experiment, we can measure a volume of flow and divide it by the time over which that flow took place. Watch the data collection here and record the volume of flow collected and the time over which it was collected. This is the popular bucket and stopwatch method of collecting flow rate measurements. Lastly, we'll show a sample of the porous media for which Darcy's experiment was just performed. Your TA will provide you with measurements from the second and third constant head experiments, corresponding to sample 2 and sample 3 shown here. We'll now move on to the falling head experiment, which is often the more appropriate setup for accurately calculating hydraulic conductivity for finer-grained materials. In this case, the falling head experiment is performed on a permeameter packed with material shown here in sample 4. In the falling head experiment, the only location experiencing constant head is the outflow of the permeameter shown here. Record the elevation of the outflow, as well as the 80 milliliter mark, 60 milliliter mark, 30 milliliter mark, and 10 milliliter mark on the burette. In the following 2 videos, we'll show the falling head experiment twice. In each case, you want to record the elapsed time as the water level drops between the 2 elevations shown with the markers.